Thank you very much. I'm Alex Wimbush, and I'll be taking you on a bit of a whistle-stop tour of some of the different representations there are of epistemic uncertainty. There are various different kinds of epistemic uncertainty you could deal with. In this case, I'll be taking you through some of the ways of representing uncertainty about fixed but unknown values. So if there's a parameter or if there's a coefficient that you're trying to estimate but is unknown, it's not varying, it's just fixed, but you don't know what it is. That's what we'll focus on here. I'll run through a case of just a sum of three unknown variables, and we'll start with a case where you may know what the minimum and the maximum of this variable could be, but you may not have more information than that. So one way you could go about doing it is modeling each of these variables as a uniform distribution in a probabilistic sense. You can do that. There are some funky things that come up as a result of doing so. If you're happy with those assumptions, you can run with this. But for example, in this case, the three values are modeled as uniforms. If you sum those up, you get a distribution at the other end that is itself not uniform. It's had some element of certainty added to it. And the more of these uniforms that you would add up, the more certain you would be in your outcome. If you're completely happy with the probabilistic interpretation, that is technically a valid output, but it's a very unintuitive and odd outcome. One way we can get about this is through the use of intervals, and we've mentioned intervals already. Intervals are literally, if all you know is the lower bound and the upper bound, that's all you know. You can use that and you can compute with intervals. There's an arithmetic for doing so. Often it's quite nice, often it's less nice, but it's more computationally efficient than trying to do so with Monte Carlo. If you've got those bounds, those are rigorous bounds, you can run those through with interval arithmetic. So that's great. Also, there is a software package that a colleague of ours has been developing, or colleagues of ours have been developing in the Institute called PBA, Probability Bounds Analysis. You can use this and you can perform calculations. It's as simple as you see on the left. Obviously, adding three intervals together is going to be very easy, but it scales quite nicely. So that's great, but you've only got information about those endpoints, and where have you gotten those endpoints from? Perhaps it's expert elicitation, perhaps you've pulled them out of the air. The analysis is as robust as those intervals themselves are. Often we want to do more than that. We want to be able to say something about tail risks or about relative likelihoods. So probability boxes, whilst not necessarily being a way of representing epistemic uncertainty about a fixed parameter, I thought I would introduce them at least. They are effectively an envelope of probability boxes, so probability distributions. So rather than one precise distribution where every value has a fixed cumulative density, you don't know what that cumulative density is. You represent that uncertainty with a probability box. So you'll see they have a left bound in red, a right bound in black. It could be any distribution within those bounds. You don't know what it is, but you can work with these structures. You can cut them into levels, use interval arithmetic, and you can get an output like you see on the bottom. You've got some of the same issues you've got if you're trying to use this to model epistemic uncertainty about some fixed parameter, as we had with probability distributions before. But if your epistemic uncertainty is around the parameters of a particular distribution you're trying to infer, probability boxes are a very, very useful way of characterizing that uncertainty. Although accounting for dependence does begin introducing more and more complexity that you need to be careful with. So p-boxes, again, in pba.py, you can run this, and it's, again, fairly simple. You can see on the left. Again, it's an addition. It gets more complicated as you use more complex functions, but it's easy to get started with. And the standard in PBA, the standard with interval arithmetic that we generally use is to use what we call Frechet bounds, where you're making no assumptions about dependence. And that inflates the bounds that you're working with quite a lot. But that should be the kind of the safe default state of not having to make any assumptions. It might not give you nice tight bounds, but it's a safe assumption to make. So yeah, p-boxes are great, but they're not specifically for modeling uncertainty about a fixed parameter. So what can we do in these cases? We can use confidence distributions. Confidence distributions you may have heard of, you may not have heard of. If you've heard of a t-distribution, that's basically a confidence distribution. You use them to generate confidence intervals. And these specifically have very nice properties of they are guaranteed to bound the answer that you're looking for with some desired probability. That gives you some ability to say, okay, it gives you confidence in your statements about epistemic uncertainty. You're essentially taking epistemic uncertainty and expressing it in an aleatory form. And if you don't have a lot of data, you get very wide intervals. The more data you collect, you tighten that up until you get towards your precise answer. And similar to p-boxes being an envelope of probability distributions, confidence boxes are similar for confidence distributions. Generally, you would find them for discrete data, but it's a similar thing. You can use them to draw confidence intervals. You can calculate them with them, as you can see in the bottom. It's just another way of representing uncertainty about a fixed point. So you can take the intervals from all of these, and as you can see, the middle one and the right one, 2 out of 5 and 20 out of 50 is representing the same ratio, but there's much more certainty in the box on the right, and that's reflected in how tight your answer is. And again, C boxes and confidence distributions are partially integrated into PBA. The canonical example of the Klopper-Pearson distribution for modeling probabilities is integrated, but you can bring the others in by just using T distributions, for example. And one nice way of representing this epistemic uncertainty is what's called a Birnbaum confidence curve. If you just take confidence intervals, stack them all up, you get a nice curve. And this is analogous to, some people would look at this and think fuzzy structures or a possibilistic structure. They're essentially the higher point, like a probability distribution, the higher points are more possible. Those are your most likely suspects. And the more data you have, the tighter this reduces. You cut down the possibility of it being other values than the one you're looking for. And if you're calculating with these, as you introduce more and more inputs, you're not cutting down your certainty. You're not generating certainty out of nothing. If you have lots of inputs, you will end up having uncertainty coming because you have lots of inputs. And handily, there is a nice, cheap, relatively easy way to get some kind of probabilistic information out of these structures. These are stacks of structures that you see, but the bottom one is constructed simply by taking confidence intervals from the top structures, running those through, and using that at the same confidence level in the output. So if you want a 95% confidence interval on your output, all you have to do, you don't have to do any Monte Carlo, you don't have to do any faffing around, just do 95% confidence intervals on the inputs. That gets you what you want on the output. If that's all you're interested in, that's all you need to do. And this plot on the left is kind of an assessment of how well that does in terms of coverage. So if you want a 90% confidence interval, ideally, you want that confidence interval to be giving you the right answer 90% of the time. And the graph on the left, if it's above the diagonal line, it's giving you the correct answer more than that value. But that's not too bad. That's conservative, but at least you're not being conned out of uncertainty. And you can see in the worst case, this is an evaluation of 200 different scenarios running through just the sum we had before. In the worst case, the coverage is pretty much bang on what you are wanting to get from it. So the worst case that you're getting is the coverage you would expect. It's a nice, simple way to do it. I think this, still working out what the limitations of this are, I suspect that it's for specifically operations on epistemic uncertainty. When you're dealing with mixtures of epistemic and aleatoric, you need to bring in p-boxes or possibilistic structures that have a more nuanced interpretation than this. But for specifically epistemic, all good. For example, the Bouguer range equation that we had brought up before. For simplicity's sake, I've assumed that we have a bunch of values that we've tried to assess that have some normally distributed error, simply because the normal distribution has a nice confidence distribution we can use to get valid confidence intervals. So all we do is generate some data. We generate our confidence intervals. You don't need all the structures above, but you can see, for example, the second one from the left. That's an example where it failed. The blue lines represent the confidence interval. The red line is where the true value is. That one failed to bounce true value. You're going to get some of those. But propagating these through with naive propagation, you get the structure on the bottom. And again, if we wanted a 95% confidence interval on the output of this Propagation equation, all we have to do is do one evaluation using a 95% confidence interval in each of the inputs, and that gets us what we want. We don't need this whole structure if we're not interested in the whole structure. And again, just looking at the coverage, it's very, very similar to what we saw in the addition case. This is over 100 different scenarios with various levels of imprecision or error around each of those values. And yeah, it gives you good coverage. It's an excellent jumping off point. It's very easy to get what you want. But if you have information around, for example, dependence of the errors that you're getting, you can possibly use that to begin tightening your answers. But as a cheap starting off point, it's good. So they have some caveats. They do require that your inputs are valid confidence distributions, and there are an awful lot of confidence intervals out there that have limitations and caveats to them. So there is some care required in making sure that the inputs work as you would expect them to. They are defined by the worst possible case that you could encounter. So generally, you can see, generally they are going to be a little bit conservative. If you don't know when you're in that worst case, then there's a question of how do you tighten it in that case. If there is information you can use, you can possibly use that to improve the conservatism of the output. So thank you very much. Apologies, that was very, very, very quick. Does anyone have any questions?
How much does the complexity of the underlying model impact the ability to propagate those uncertainties?
It can impact it enormously. When you're starting to deal with, like the Propagation equation was a wonderful example to run through with this, specifically because it's a single-use expression. Each value only occurs once in it. That means it's very cheap, very easy to run through. When you start dealing with equations that have dependencies within them or multiple repeats of the same values, depending on the level of knowledge that you have, if you know it's monotone of the input, you can start looking at endpoint analysis to try and deal with things. But a lot of the cases, you won't know that. Then you start having to introduce, if you have no knowledge of what's going on in the function, if you're propagating intervals through it, you are likely to get a very, very conservative, like an enormously conservative answer. I don't think that's strictly the case. I think there are cases where it can be too narrow, but what you can do, there's techniques like subinterval reconstitution, or there's fancy Cauchy deviate methods for more complex functions that, yeah, you're starting to stack on layers of computational cost, but compared to a Monte Carlo simulation, it's much easier to run through and easier to get visibility of those tail regions. It's not like, it's by no means easy, but it's a lot easier to get at specifically the information that you want to know.
That means it requires intrusive knowledge function. You're dealing with a pure black box or a grey box, and tell roughly what's going on inside, and the details. It can be typically just one column.
Yeah.
It's okay. But there are strategies to use. That's the case. So,
yeah, I don't have an enormous amount of experience pushing it through black boxes myself, but I know there are methods for, because it's all based on interval arithmetic, there are methods for using interval arithmetic with black box functions.
can I just clarify something I thought you said earlier in your presentation, which was wanting the group of uncertainties put together to give you more certainty. Did I misunderstand you?
You did not misunderstand me. One of the initial cases was if you're modeling, if you know the bounds and you're modeling the uncertainty around these fixed values as a uniform distribution. So you're saying, well, all possible values within that range are equally likely because I don't know anything else. If you actually perform probabilistic analysis over those distributions, you get an output that can start actually having some certainty in it, despite the fact that you're trying to model a lack of uncertainty. And in this case, it's not so extreme. Sorry, I'm pointing to this. In this case, it's not so extreme. If you were to add lots of these together or perform some functions over lots of these inputs, you actually get quite a tight distribution on your output. And the question, that certainty comes from assumptions about the dependence of the way you've combined these inputs. I guess, if you're happy with this model for your inputs, what you should be doing, unless you have knowledge about the dependence, is propagating them through with no assumptions about dependence. And then you would get a P box rather than a precise distribution.
Okay. So we can thank you. I just comment there on this specific example. Here what you have essentially is you're trying to sum two intervals between 1 and 2 and 4 traces, right? But because you've injected your own knowledge, every value between these values equally likely, you don't end up with a range, so you end up with a triangular distribution. You've injected some extra artificial knowledge. That's what that precise curve is going to do.
It's like
something you don't have.
Like if you had like a go-no gauge, like like lower and upper bounds on like what the diameter of that hole might be, but you could maybe say, oh, it could be equally likely to be anything in between there, but it might depend on the operator who made the hole, the condition of the bit that made the hole, the reamer. You're making an assumption saying that's all equally likely, which is actually a strong assumption to be making, and this is the impact that assumption has.
That sounds very important to me. Are you the only one worried about it? Not at all. So maybe we should go on to our next speaker. Thanks again.
Thank you.
I won't bring